Today we're going to go over U substitution, which is a way to integrate composite functions. You simply declare a variable as U, and you want to make sure that that variable, at least the majority of it when differentiated, is present in the function, or in the integral, I should say. And then after you've found U, you want to differentiate U, you want to plug in U and the derivative of U, and then from there you want to integrate. Okay, I want to work through this one with you guys. You may notice that x when differentiated, or sorry, x squared plus 1 when differentiated is equal to x. And with U, I should have stated this earlier, you want to gather as much as possible, if that makes sense. So any constants, you should always include that in U. So yeah, we may notice that x squared plus 1 when derived is almost equal to x. Not quite, as you can see, because it's actually equal to 2x. So first, let's state that U is equal to x squared plus 1. And then we want to differentiate U. And we end up with 2x. So for the meantime, let's just plug U into the equation. We end up with x over U dx. Oh, I should have put dx over here as well. You should always do that when differentiating, at least in U sub. And so these are almost, we can almost get rid of the x and the 2x, or sorry, we can almost get rid of the x and the dx. Those are almost equal to x squared plus 1. Of course, we could just set we could just set x dx equal to 1/2 du, which means we can replace x dx here with 1/2, and we can take this constant out of the integral, 1/2, 1 over u du. And you can clearly see here that 1 over u du, or 1 over x dx, anything in that form is equal to natural log u. So we end up with 1/2 natural log u. And from here, we're almost complete, or we've almost finished. We just want to plug in u. Oh, I forgot, since this is a indefinite integral, we have to add plus c. So from here, we can just plug in u. We end up with 1/2 natural log x squared plus 1 plus c. Oops, I forgot to put plus 1 plus c, and that is our final answer. Okay, so that was just a practice problem. Hopefully you've learned that integrating is just essentially the reverse chain rule. But let's move on to this problem here. It looks quite difficult, but let's just equate it to something simpler. 2 times 2x e to the power of x squared plus minus 3. And when declaring the u value, you should always essentially differentiate it, and then don't worry about any of the constants. Simply look at the values. If there's one x value, or if there's one function with x that is a higher power than another function with x, then you can simply declare the higher function, the one with a higher function, as u, which we're going to do in this case, because you can see that if we didn't differentiate this, we end up with 2x. So we should say that u is equal to x squared minus 3. Du is equal to 2x dx. And so we can plug in u. We end up with the integral from 0 to 3, 4x times e to the power of u dx. But we still have a dx, and we still have this other x over here, and so we can't integrate yet because we aren't in respect to x. So just to make this simpler, I'll write this out. What can we do to equate 4x dx to 2x dx? Well, we can simply say that 4x dx is equal to 2 dx. And so we can replace 4x and dx with 2, and we can draw 2 out of the integral because it's a constant. So we end up with 2 times the integral from 0 to 3 e to the power of u du. Now, e to the power of u is simply equal to e to the power of u when integrated. So we end up with 2 times e to the power of u, which in this case is x squared minus 1. We don't need to add plus c because this is a definite integral. Okay, sorry, I'm kind of running out of space here. We can just plug in the 3 so that we end up with 2 to the power of 6, 2 times e to the power of 6, I should say, minus 2 times e to the power of negative 3. And that is our final answer. Okay, so this question looks similar to the practice problem 1 that we went over. Although it may be past your expertise, we are going to go over inverse tricks. But that shouldn't discourage you. You may see that it's impossible to declare u as x to the power of 4. And that's simply because if we were to differentiate it, we would end up with 4x cubed. And that's obviously to a higher power than what x is equal to. So instead, let's just make this easier on ourselves. And let's simplify this such that we end up with the integral from of x over x squared plus 1. And now we can see that this is almost in the form of arcsine being 1 over x squared plus 1. This is equal to arcsine. And so we can just declare x squared as u. And that will allow us to get rid of the numerator. So we say that u is equal to x squared, du is equal to 2x dx. So now we end up with the integral of x over u squared plus 1 dx. And we're almost in the correct form. However, we can't, since we have dx, we can't integrate with respect to x. So how can we make it such that x times dx is equal to some form of du? Well, we can just say that 1/2 du is equal to x dx. And so we can simply equate this to 1/2 the integral of 1 over u squared plus 1 du. And this is already, thankfully, this is in the form of arcsine. So we can, arctangent. I may have said arcsine earlier. I meant arctangent. So we can say that this is equal to 1/2 arctangent of u. Of course, we have to say it's plus c because this is indefinite. And we can simply plug in u. So we end up with 1/2 arctangent of x squared plus c.